Picture this. You're building a model that is able to distinguish between oranges and apples. You collect a data set of, let's say, 100 pictures. You train the model and it does okay. You test it, but it's doing horribly wrong. You ask someone and they tell you, well, of course, it's doing bad. 100 images is nowhere near enough data to train a good model. Just add more pictures. You go back to your studio and you gather a bit more images. Let's say you reach 1,000 images now. Your training accuracy is doing okay, your testing accuracy is doing a bit better, but it's still really bad. You go back to someone and they tell you, well, the fact that it got better means that you just need more data, so just gather more images. You go back, you take more images, and now you have millions of images. There is no way you don't have enough data, right? You test the model, and it's still doing very poorly. So, giving up, you go back to someone who picks up your data, your models, and does the evaluation for you. And you notice that the first things they do is they check the distribution of your data set. And they find out the flaw fairly quickly. They tell you that the model is just training on very poor data. But how? You have so much data, right? And so much data is supposed to make it better. Not really. When you're looking at the data set, you realize that the studio you took all the images in had very bright light conditions, say in the morning when you were taking all of the Apple images, and then when you were done and it was a bit evening time and it was a bit darker, you were taking all the orange pictures and then the lighting conditions were a bit dimmer. And that caused the model, instead of learning about the nuances and the features between your fruits, to only learn that, well, if it's bright, it's an apple, if it's dark, it's an orange. However, when you look at their testing data set, you realize that it's a bit more diverse. That means different colors, different backgrounds, different formations, different types of the apple. And this is why, because of this distribution shift, your model is doing very poorly. So in reality, just adding more data set from, let's say, the same distribution just caused your model to do worse and not better. We're going to break down in technical aspects what data actually does to a model, and we can talk about how bad data or biased data can actually derail your model to a very different direction than what you were hoping for. So let's dive into it. When we're talking about machine learning model and data, we're usually talking about pattern recognition. And with any pattern, in order to identify it, you need enough examples of that pattern. For example, to build a model that is able to identify any cat, you need enough pictures of cats, let's say all the pictures of cats you can find, in different environments, different backgrounds, and different scenarios, so you can figure out what patterns make up a cat. Similarly, to build a very strong language model, you need a very long corpus of data sets that will teach the model what the pattern of text is. This means enough text to learn grammar, this means enough to learn contextual relations, and just to remember and learn what words usually come after which other words. Our training data learn the boundaries of what your AI model learns to do. If you only use old age English to train a model, it will learn to talk as if it's in one of Shakespeare's old plays. If it sees text only in a certain language, it will not understand any other language. And finally, if we only use furry cats as images, we might not be able to distinguish hairless cats. You get the point. The key idea here is that data shapes our model's behavior and not just their accuracy. It shapes the way the model responds, its behavior, what it prioritizes, what it misses out on, and what it ignores. So yes, every machine learning model needs data to thrive, but the wrong kind of data can just make it worse. While data is very important in training, and possibly the most important aspect of it, choosing the wrong type of data can derail your model and push it somewhere entirely wrong. You might be wondering, if we're gathering millions of data points, we are possibly gathering all possibilities, right? And maybe if you gather enough images, you will have just about enough of everything, but that's not always the case. Let's remember that data collection done properly is very time consuming. It's actually the hardest part and the most time consuming task in any AI project. Collecting data ethically and properly to ensure that it's clean, balanced, unbiased, and diverse enough to cover the entire distribution is a fairly hard task. So let's break down some of the problems that AI builders and developers face when they're building their own models when it comes to data and see what we can make out of it. The first problem is redundancy and diminishing returns. Redundancy, as the name suggests, means that you're building a lot more data that you don't really need. Diminishing returns hint to the fact that after some point, you will stop adding any meaningful information. Let's tackle an example where we're trying to detect street signs. Imagine that you get the same street sign, you get multiple pictures in the same condition from the same angle without really changing that much. After some points, this data set has a lot of redundancies that doesn't add any more new information to the model. And this is why it's called diminishing returns, because after every images, you just get less and less information every time. You get less and less benefit with every image. However, what you do get is a lot of computational resources because with every extra image, that means a new set of calculations that you need to do. Now, let's be clear. Some datasets actually require this form of treatment. For example, if we realize in our dataset that we have one class that is the 40% the size of every other class, we have two options here. Either drop 60% of all other classes to make sure that they're all balanced, or make sure that we add images to our one class to make sure that it's as equal as or close to all the other images, and sometimes a mixture of both. Now, if we can collect more images, it would be easy. But like I said, this is usually one of the hardest things to do and it's more time consuming. So what people tend to do is that they would augment the images, meaning that I would take an image that I already have in my data set and I will start adding stuff to it. This includes changing its brightness, maybe making it more light or more dim. This includes adding some rotations, maybe photoshopping some items in front of my object, and cropping bits and parts of my image in and out of the picture. In other cases, we might realize that our model is overfitting. Overfitting for AI models means that it's getting really, really good at training data, that it's just memorizing the patterns in the training set, but not really generalizing to the broader distribution. Meaning that your model will do great during training, but if you test it, it will always perform poorly. Like we explained in the very first example, this means checking the wrong features. So, for example, instead of looking at the features of our fruit, it's looking at the overall light conditions of the image. And one of the solutions to fix this problem is to make sure the data is harder to find these nuanced features that we would just be able to learn the actual underlying features that we need to. This includes changing a bit in the image by augmenting it to make sure that it's not all following the same distribution anymore, but the only thing that is the same would be the features that we're looking. What this does is that it adds more images based on the original one with slightly different variations. The augmentations can be very subtle, but they also can be very extreme. And it also depends how much extreme you want to make it because you don't want to make it too hard. But this is going into different territory now. The idea is that while this is useful for some models, it needs a reason to do it. Just adding one picture of the same class multiple times takes away from the benefit of having that image being there. Overfitting is also an issue that is partly due to having too many images of the same specific features. Meaning that if you add, like we said, one image multiple times from the same angle and everything, this increases the chance that your model will overfit, meaning that it will start looking at the features that are around the object you're trying to detect and not the object itself. Other problems include noise. It's a random, low quality, irrelevant pixels or changes in your data points that might throw off the model and confuse it in its prediction. Imagine you're trying to learn from a textbook where every third sentence is a complete random gibberish sentence that has no relation to everything before or after it. Or learning from a sentence where every third word is just completely random. And as a fun fact, this is actually called adversarial attack on AI models. A lot of people have been starting to add these things to their data to stop models from training on them. So, for example, some people will start writing their blogs, making sure that every few words there's a random one. Some people will start adding random noise to their drawn art to try to attack any AI that tries to learn on that data by stopping it. And while there are some denoising methods to take in some, let's say, input with a random noise inside of it and clean the noise outside, these methods are an extra computation step that you don't want to do before the model. It depends on how noisy the data is and how much you want to clean it. But it's also very specific to what kind of input it is and what kind of output you're expecting. Sometimes if the adversarial attack, the noise is too hard, even your denoising algorithm may just ruin the picture entirely. And this is not what you're looking for when you're training on a clean image. Which of course, brings us to one of the biggest problems, which is scaling. With more data points that you add, you scale exponentially the amount of computation and energy you need to train your model. So even if we manage to denoise and clean and make sure that our data is of good quality, we tackle the problem of computation, of infrastructure. There is so much energy that we need in order to train these models. A lot of people are already talking about the computational resources needed to maintain and keep these models active. AI training requires massive amounts of electricity that can cause infrastructure damage, but also increased stress on all power grids. And this is partially due to the ever-growing sizes of modern neural networks, but it's also due to the growing size of dataset that are needed to accommodate for the growing size of the machine learning model. You see, if the model is too large and data set is too small, the model will be too complex and it will overfit on the small data, meaning that every time the model grows, we need more data to train it. Now, you might say, why not just never grow our models? Because smaller models also have limitations. There is enough parameters to only learn a few things. So eventually, the only way to learn new information is to grow the model. But now that the model has grown, you also need to add more data to accommodate for that growth. And this just keeps going indefinitely. So yes, extra data is a solution to most problems that you might face with your model, but it's not just about adding any random set of data points. It has to be a clean, diverse, unbiased, and you have to make sure that it doesn't unbalance your data set. You have to make sure that it doesn't have any noise. You have to make sure that you're able to scale properly for that new data set. There is a study done in 2025 by researchers from Harvard, Princeton, and Stanford universities titled Overtrained Language Models Are Harder to Fine Tune, which is a very self explanatory title. It explains that language models that are trained on very large corpus of tokens are actually very hard to fine tune later for smaller tasks. Actually, training your model with more data can lead them to becoming worse. In this study, they tested a model with 3 trillion input tokens against a model trained with 2.3 trillion tokens. Now, we're talking about a lot of tokens difference here. And they saw that the model trained with less tokens were 3% better on testing benchmarks. The authors even went on to call this catastrophic overtraining, meaning that you're training on so much data and overdoing it that the model finds it hard to learn new information or to do better, leading us back again to the diminishing returns talk. They noted that for language models, there is a set inflection point where adding more data to that point just makes the model more fragile and easy to break and not that easy to fine tune anymore. Multiple papers also noted that it's very hard to fine tune models or very hard to keep models working properly when offered a very large context, especially if that context is irrelevant. Researchers at IBM specifically noted that there is a set size for the context window where adding any more information after it actually leads the model to information overload. This means that LLMs miss crucial details or become biased to more information in the beginning or the end of the context and not the real information in the middle. The researchers called this prompt stuffing, where even if the context of the model allows for more information, just getting to that context point becomes too much information for the model to use effectively. The truth is, most AI models need more quality and good labeled data than they do need a lot more data. Let's talk about labeling. In previous episodes, we talked about supervised learning, where most models we know today in modern neural networks need some ground truth or golden reference of what they're expected to predict. When these labels are wrong, the models learn wrong things. They learn wrong relations between different inputs to different outputs. A mislabeled image of a wolf tagged as a dog might seem like a very tiny error until the model decides windy backgrounds with ice means dog, which is not really what we're looking for here. Not in both cases, right? Because a wolf isn't a wolf because of his background, and a dog isn't a dog because he was tagged in one of the images as a wolf. These small errors actually scale quite fast. They lead to our models in real life scenarios to misdiagnose diseases entirely, or see a normal conversation as a hate speech, or the other way around. For example, let's look at an object detection model. Every object detection model needs a bounding box as a label, meaning that whatever we're detecting is inside that box. The model learns not just the class of whatever is inside the box, it also learns the position of that box, the size of it. So let's assume that for a certain class, these boxes were slightly bigger than they're supposed to be, or slightly shifted up, left, right, down. The model might start to not figure out what it's learning, meaning that it would always be biased towards pushing the box left or right, but it will also be looking at different features. If the model is bigger than expected, instead of only focusing on the features of the object we're trying to detect, it will start looking at features in the background, which is not what we need. Similarly, if the box is too small, we might be missing out crucial aspects of what makes the object itself. Usually, labeling is done by domain expert, meaning that we expect the model to be supervised by people who specialize in whatever field it is that it's supposed to predict. However, with the growing size of data, everything now has a capacity to create and gather more data. It's becoming very hard to make sure we can label all of that data by domain experts. So we start to gather people who are not really domain expert but have an idea, hoping to finish the labeling quite faster. Another case might be that you're building your own project, maybe it's a side project you're working on, and you don't really have access to any domain experts. Or maybe you're trying to build something as a proof of concept so that you would convince the domain expert to help you, which means that you might need to label the data yourself. Companies use tools like Amazon Mechanical Turk to pay people small amounts for labeling thousands of data points a day. And this is where human error creeps in. See, humans are erronists. We make mistakes. We can get tired, we can miss context clues, and we can just label stuff wrong by mistake. We also can just not be sure about what we're labeling. We might disagree. What I think might be a certain label, you might disagree and think it's a different one. What I believe is the minimum inbounding box of some object you might believe needs to be bigger, smaller, or a bit shifted to one direction. So the label quality just depends a lot on the people who are doing the labeling. But not just that, it depends on who's evaluating the labeled data points. Because while all the labelers might agree on a certain label, maybe the evaluator believes that it's wrong. It also depends on what tools and what instructions are given to the people doing the labeling. So while most of the talk in today's world is about the size of the model, the architecture of the model, and the training hours and the energy, a lot of it is about the human work. A lot of it is about the labeling and the data we use. The real work often boils down to the messiness of human nature. Whether the data we prepared was unbiased, clean, and properly diversely distributed across our data points. A lot of AI projects fail before the data even hit the model, before the model even goes to production, because the data was not done properly. Let's take a small detour and talk about types of data. Different types of data actually teach the model different things. In language models, for example, data comes from social media posts, articles, blogs, Reddit threads. It carries a style and an underlying bias. There is also a big difference between structure and unstructured data points. As you'd imagine, structured data is data point that has a clear, structure. This includes spreadsheets, tabular data, data that has a clear input to output values, often things that are easy to calculate and are deterministic. Structured data is organized and highly predictable. It's usually, like I said, in Excel sheets or tabular data. For example, it's very easy to assume what the price of the house is, knowing the size of the house. There is a clear relation between the house size and the house price. Unstructured data, on the other hand, is messy. It's unstructured. It's like audio clips, videos, images. And while some of you might think that an image with a clear label is a structured, well formatted input, it really isn't. For example, like we said, you can really distinguish the relation between the house size and the house price. But in an image, it's not easy for the model, it's not easy for the AI to find the relation that is the house size and the house price. The pixel formation, the colors that the model sees, is not the same as we interpret it. The features that it looks for is still something that it has to learn. It still has to figure out what features to look for, where they are, or what is the relation between different features being next to or not next to each other. So why does that matter? Models today, most modern neural networks are trained on these unstructured data. In fact, structured data is often only used for traditional machine learning techniques that were used way back in the day. While some of them are still being used today, most of the AI we hear about is trained on and is inferencing on unstructured data points. They absorb how people write, talk, express emotions, and just do their own thing. They absorb all of this information and make up their own inference or information out of it. This is especially true for language models. They absorb the tone that is in the data they were trained on. If you train it on enough cooking blogs, they might come out as friendly and cheerful and only talk about baking and cooking. Well, unless it's a Gordon Ramsay blog. But what if we want to take a model trained on these certain information and use it in something entirely different? Is it possible to take a model trained on, let's say, cooking blogs, but repurpose it for academic research? Or a model that is very good at detecting birds, and we now want to use it at detecting planes? Of course, the closer the two tasks are to each other, the easier the task is to move or repurpose the model from one task to the next. But in most cases, it's highly doable. And this is where fine tuning comes in. The idea is that assume we have a model, a language model trained on a large corpus of data set. Now, this model, because it saw a lot of text, is already good at defining the probability of what words come after each other, but it's also very good at understanding context and, more importantly, good at understanding grammar. Now you need less work to learn about these information because you only want to repurpose it for something else after the step. So you need less data points that are more specific. The model, for example, trained on detecting birds is already good at detecting features like the sky and when something is on the ground. It is also good at detecting features like shapes and colors, meaning that the amount of work you have to put in to now repurpose the features it already learned into detecting the differencing is easier. So as soon as you have a model that is already trained on a diverse data set and is able to extract, let's say, different features, it's very easy to now feed it your specific data set that still has to be clean and diverse and everything, but it's now smaller. And you train the model to steer it directly into your own different direction and task. Now, of course, this can get a lot more complicated. It depends on the task, it depends on what the model was doing before, how it was trained, and how it's structured, and what the new task is, and how the output is structured. But you get the idea that it's possible. It's also very important to note and remember that fine tuning, while steers the data and the outputs of the model to your directions, the thing it learned isn't completely erased. The stuff the model learned will always be there. Otherwise, you would have to start over from scratch, or you would assume that all the knowledge before is gone, and hence the reason you're fine tuning the model goes away as well. So let's look at case studies, stuff that actually happened, to put stuff into perspective to what happens when the models are trained on bad data. The first story we can talk about happened in 2016. The headlines read that the chatbot turned toxic. But what really happened? Microsoft had launched Tay, a conversational chatbot that was meant to be launched on their Twitter page to learn as it interacted with more users, meaning that it will interact with all users, and as it chats more with them, it will learn more about what it should say and what it should do. The idea sounds good on paper because it will learn how the users likes it to respond and it will respond equally. However, within 16 hours of going live, they had to shut it down. It only took 16 hours to realize that it was a complete disaster. As soon as it went live, the internet showed Tay a completely darker side of humanity. Users began intentionally spamming Tay with racist comments and toxic slurs. They became very offensive when texting the model, and because the model was trained to take whatever the user said and repurpose it into learning material, it started taking in the same information. Not just that, it started posting stuff about it itself. So within hours of launching, it started learning these same offensive, racist, and wrong prompts and repurposing it into its own posts and its own comments when responding to actual users. So this happened because they never really had any guardrails. It didn't have any filtration step and no real safety precautions to ensure that the data that the users enter will not be directly used in training without any changes. It also really underlined the truth that no one wants to talk about it, is that in order to train good AI and in order to understand AI behavior, you have to talk about human behavior because most AI data is generated by humans. In 2015, just a year earlier, Google faced a different but equally disturbing problem. They had just published a new method, a new AI model that would distinguish different people, objects within an image in order to tag them properly. A black software developer using Google Images to organize his photos realized that a picture of him and a couple of his friends was marketed as gorillas. Being very disturbed and raising issues, people realized that this is happening with a lot of other black people. What they realized is that Google's data set that they used to train this model underrepresented people of black color, meaning that they couldn't have enough data points to represent black people, so that most black people was just targeted as gorillas rather than people. As a result of this unlabeled and bad data set, the results were not just wrong, they were also offensive. Google, of course, responded very quickly, removing gorilla as a label, but also rolling back the new update. But this doesn't change that the mistake has already happened. But even now, today, the reports say that Google is still keeping the tag of gorillas off, not just because they're unsure if the model is now trained properly, but because they cannot handle a new offensive output. Now, of course, the models weren't meaning to be offensive. The developers that build these models weren't meaning to be offensive, at least I hope not. But it just shows that even without any ill intent, bias can still creep in and ruin your model outputs. It also shows that even large companies can make very wrong mistakes if they don't take the proper steps into making sure their data sets are done properly. These cases show that preparing good data isn't just a bug or something to be overlooked, it can actually cause actual harm. Let's take a step back and look at the bigger picture, specifically in today's world. We know that there is an ever-growing size of data in today's world. Every app you use, almost every app you download, asks you for your data before you even start it up. But do you know, or do people know, when their data is being used to train the model, or if they're being used in any way? You actually don't. Most large language models and art generating AI is trained on images and information that is widely scraped from the internet. This includes any publicly available information, whether it's images, blog posts, articles, code repositories, and so on. But just because something is available online doesn't mean the people who posted it accepted it being fair game. When you post your image or your blog on a social media platform, you don't expect that information to be used in training. But in reality, artists, programmers, and just private individuals have had their data scraped and trained on without their prior consent. Their data becomes part of the training, becomes part of the AI, without them being notified, accredited, or even told. And this, of course, starts a legal and ethical question debate. Like, who consented for this? Does adding a secret hidden clause in the terms and condition allows the company to do this? Can you just opt out and have your data not be part of the training? And who is profiting from this data? And this isn't new. Getty Images actually sued Stability AI for using a lot of their watermarked images. Millions of their images have been used in training. And they only found out when the AI started generating images with the same watermark. And then they were notified that in order for that to happen, the data has had to have been used in training, but they never consented to this. Similarly, some artists realized that a version of their signature is showing up on AI generated art, but they never consented to having their images being part of the training dataset of any AI model. Also, New York Times sued OpenAI and Microsoft for using their journalism output and articles in their training without licensing. This just shows a broader cultural shift. Data isn't just neutral, and using data means inheriting some of the emotions and feelings that were written behind these datasets, meaning the model inherits this information, and whoever created the model needs to inherit the responsibilities of using these data points. In today's world, We see platforms like ArtStation or DeviantArt actually add tags like no AI, and it's trying to protect people's art and making sure that the data isn't being scraped and used for training. On the other hand, the Oscars are debating whether an AI generated content or AI assisted filmmaking can be awarded with rewards. And the truth is, there's going to be an even wider shift as the world figures this out on their own. The only question is, which side are you on? However, this will be all for today's episode. We have covered a lot of information today, but the most important part of today's episode is to understand that while data is useful for every model, maybe even the most important building block for your AI, more data doesn't just mean a better model. The data you pick, you curate, and you clean is important for your model. Your model is based on the data you use and the feelings and information behind the data. Always remember, it's not about the quantity of your data set, it's about the quality of your data points. Let me know what thoughts and ideas this episode sparked out for you. And remember, stay critical, ask a lot of questions, especially when it comes to AI models. In our next episode, we tackle thoughts and feelings, and whether AI models has already reached emotions and have figured out how to use it by themselves. Be sure to subscribe and send these episodes to whoever is interested. Until then, stay curious, and I'll see you in the next episode.